unless you delve into the details. So I wasn't able to delve into the details in my talk last month. I'll do it this month in the news summary. So here is let me go back. Here we're going to go into this region right here on the left pillar, okay? About 2/3 of the way down the left pillar. And on the left, you see the 1995 image. And on the right, you see the 2015 image. And you can see that the 2015 image has twice the resolution. We had 1/10 of an arcsecond resolution in 1995. We have a 20th of an arcsecond resolution in 2015. And you can see it's just that much crisper. All right, one of the results of the 1995 scientific papers was that these yellow regions, this ionization front, were as thin as Hubble could resolve. You know what one of the results from 2015 is? They are still as thin as Hubble can resolve. These ionization fronts are the regions where the dense molecular gas turns into the rarefied ionized gas, okay? Ionization, the process where high energy hits the atom and the electrons are removed. That's the ionization process. Well, you can see that ionization front is really as thin as Hubble can resolve it. It's still below the resolution. And I gotta say, in graduate school, you learn that the transition region is really, really thin, but to see it visually is really kind of cool. Now, if we look at the central pillar, in 1995, that was done with the PC chip, the planetary camera chip, which actually had 1/20th of an arcsecond resolution. All right? The WIF-PIC 2 had 3 chips that had 1/10 of an arcsecond resolution, and then 1 chip that had 20th of an arcsecond resolution. The pixels were all down at a smaller angle. So you can see that some of the detail here is reflected here. But you can see that the signal to noise, the improvement in the detectors is a lot. You can see there's a lot of, oops, let's go back, a lot of noise in here that you just don't see in here. So the structure that you see is improved not just by an improvement in resolution, but by an improvement in the detectors and the efficiency of those detectors in getting the light from distant cosmic objects. I also like this little object up here. You see this? We'll call that the jellyfish. All right, that'll come back later on in just a bit, okay? Finally, we're going to go up to the top of the left pillar and the place where all these stars are forming. And again, on the left is 1995, on the right is 2015. And again, just that much more detail, looking at the structures that are forming, in which stars are forming. These little fingers here, these are places where dense objects and stars may be forming inside them. Now down bottom here you see this jet here, and that is a signature of star formation. Now I like to call this a birth announcement, because as a star forms, material is flowing and streaming onto that star from a disk, and other material is then flung off in these oppositely directed bipolar jets. All right, and you can see the jets streaming out from a newborn star. But here's where you can really see, because I've blown this up a lot, the resolution difference between 1995 versus 2015 in the resolution of that jet. The other cool thing about that jet is we actually saw it move. The jet's material flowing away from that newborn star was here in 1995 and moved to here in 2014 when the picture was imaged. I'm calling it the 2015 image because we released it in 2015, but of course we took the data in 2014. So in the 19 years, you can actually measure motion of that material flowing across the nebula. Kind of cool. All right. So there are some other things, of course, that's just a comparison between those two images. There are other things that appear in this image that, of course, don't appear in the other image. In particular, you get to see what the bottoms of the pillars look like. And you can see that they actually flow out. That we talk about the stars way, way up here, that their ionization and winds are streaming down, streaming across these pillars, creating these pillars, but here you can see the material streaming down. Matter of fact, a friend of mine who likes science fiction looked at this and said, "Oh, I know what that is. This pillar, it looks like the Dementors from Harry Potter." All right, the sort of flowing gaseous effect that they used for the Dementors in Harry Potter. Also at the bottom, you can see an amazing arc of yellow ionizing emission, which usually I expect the ionizing emission to be along the ionization fronts. I'm not exactly sure what this is. I'm not a specialist in star formation, but it really caught my eye as something cool, as well as these tiny little pillars off in the lower right corner of the image. Our image processor Zotlave calls this mini-me because it looks very much like it's these tiny little pillars. These pillars and things appear on all scales. The other thing we got to do with the 2015 image is not just do visible light, but also do an infrared version of it. Isn't that kind of cool? Let me go back. Visible light, infrared. All right. With wide field camera 3, we have we can go into the infrared. If I put the two of them up next to each other, you can see that there's a lot of correlation, but a lot of differences between them. So let's jump through some of those features again. Here is the visible light 2015. Here is the infrared. All right, and looking at the detail, you can still see the structure. Infrared light is longer wavelength. It can penetrate through much of the gas and dust and see details inside. But of course, where you see it dark in the infrared, that means where it really is these dark, dense clouds. Go to the top of the central pillar. Here is that jellyfish here. You can almost see a little bit of it here. That doesn't look like it's got a star forming inside it. Okay, it's not a really dense piece. But you can see some star formation going on in here. Looking down into the gas, you can see star formation here, which is only hinted at. You can see one of the stars here, but it's hinted at here in the visible light. Also, if you go up to the upper region of the up top of the left pillar, you can see the fingers here. Well, the fingers aren't so prominent, but if you look, you can see, oh, there you go, this star forming place here, which is not shown here. You see the red here. Looking inside the gas, you can start to see what's happening inside these pillars. Also, actually one of the more telling views is from the larger point of view. This is that left pillar, which we tend to sort of think of as being this tall, solid pillar, but we often say it's not necessarily. Well, look in the infrared. What do you see here? You can see through the pillar. What you're really seeing is you're seeing this dense gas cloud up here, and then the shadow through here. All of this in here is the shadow of this dense cloud. The ionizing radiation isn't hitting that region, so it looks dark when we see it in optical, but when you look at an infrared, you can see that the emperor has no clothes, that it really is transparent in the infrared. One other cool thing is that here is a region in optical. Take a look at these 4 stars here, because this is the very same region, okay? And it looks like that in infrared. All right, these 4 stars, here are the 4 stars that match, and these 4 stars suddenly appear out of nowhere. Really what they are is they're behind the gas. You're seeing through the gas to see these. You can see a lot more stars, and stars that glow in the infrared are different than stars that glow in visible light. Visible light, you need tens of thousands of degrees, thousands to tens of thousands, only a couple thousand degrees, and stars that are like 2,000, 3,000 degrees actually glow more in the infrared than they do in the optical. All right, so here we had 3 cool images of the pillars of creation, and just a nice little exploration to take a look at it.
How big is that?
Okay, so this pillar here is about 3 light years long. So we take that call it about 6 light years top to bottom at the distance of the Eagle Nebula, okay? Yeah, kind of cool. All right, we get one more story for you, which has sort of been preempted by our lobby display, but I call it In Your Dreams, Hubble. Okay, so this is a picture of the Great Nebula in Andromeda. I found it in a book published in 1915 from the Yerkes Observatory. This was taken in September 1901. And you'll notice this is the Great Nebula in Andromeda because we didn't know what it was for sure until Hubble came along in the 1920s. So here is Hubble's 1923 discovery observation of a variable star in the Andromeda Nebula. As you can see, he's got these N marks here, looking for novae in this nebula to see what he could see. And he had one mark that he thought was a nova, and then found out, no, it's a variable star. And the variable stars are really cool because if it's a specific type of variable star called a Cepheid variable star, the period which it brightens and dims, that time scale is proportional to its absolute magnitude. So you can measure the brightening and dimming time scale and then know how bright that star really is. And then once you know how bright it is, you can measure how far away Andromeda is. And Hubble was able to do this in 1923 and set the stage that it is not a nebula, but it is a galaxy unto itself. That this nebula is definitely outside of our galaxy. Well, Hubble's namesake telescope looked at that exact same star, we called it Hubble Variable 1, and got images like this. So these are 4 images of HV1 over the course of December to January 2010, 2011. And if we put these in motion, this is an animated GIF, you can see it brightening and dimming. So Hubble's namesake telescope has looked at the star that changed the universe. But you can see that Hubble can see what Hubble could only dream of. And in 2004, we actually did a very special field called the Stellar Deep Field when the Advanced Camera for Surveys was brand new on Hubble. And you can see this amazing image. And if I zoom into it to show you the detail, that star is in our Milky Way galaxy, and every other star is in the Andromeda galaxy. Examining star fields in another galaxy. Not just star fields, but this is a globular star cluster in Andromeda, not in the Milky Way. Look at the kind of resolution Hubble can get. But we can still do better because this image was taken way out here, way far away from the disk of Andromeda. This is out in what we call Andromeda's halo, studying the stars in Andromeda's halo. And so what we've just completed is something called the FAT survey, the Panchromatic Hubble Andromeda Treasury Program, which has looked at the main disk of Andromeda in excruciating detail. Amazing detail, incredible detail that looks like this, okay? So this is the Hubble image, and you see the jaggies here. These are the footprints of Hubble. These are the pointings of Hubble. To fully appreciate the scale of this image, you recognize that this is over 100,000 pixels across here. It's about 30,000 pixels high. It's several billion pixels total. They did 411 different pointings of Hubble, 7,398 exposures over 3 years to cover basically half of the disk of Andromeda. Well, actually, it's about a third if you can consider the whole thing. Really, the largest composite image that Hubble has ever produced. Now, I'm going to take you in to show you some of the details of it, and this is going to be at 1/4 resolution. Okay, I can't do the full resolution; it's too big an image for me to view. But this is going to be at 1/4 resolution. All right, here. So if we go into the center of the galaxy, you can see this is the core of the galaxy and all things, and it's so blown out. There are so many stars in here, you can't really see them. But if you see these white dots, those are star clusters. Those aren't individual stars. Those are star clusters. If we move a bit further out where we have the dark gas and dust, you can see the dust lanes and other things. Again, these are star clusters, and the individual stars are well, at the resolution of this projector, they're still too small to see. All right, we'll get there. I have something at the very end. We get out to the star-forming regions. All the blue stars you see here, these are newborn stars. Again, the bigger ones are star clusters. Some of them might be stars in our own galaxy. Again, seeing the star clusters. And if you get out to the really, really edge, well beyond almost the visible disk of it, you can still see that there are still a tremendous number of stars out there viewing stars in Andromeda. over 100 million stars. I believe the number that they quoted was around 170 million stars that they have cataloged here in this full image from Andromeda. Amazing detail to see. So to show you what you're looking at here, we made this image here to show, okay, we've got these dust lanes, we've got these star clusters. You can even see background galaxies through the disk of Andromeda. Some of the brighter stars will be Milky Way stars. And over here we have a star-forming region, again, more stellar clusters and dust lanes. But you see those words, star-forming region? We're going to go into those at full resolution, and you can finally start to see the stars. This is one that actually is full resolution at the full thing, and not the quarter resolution I was able to show you in the previous images, but the full resolution to see the amazing detail of the structure in Andromeda. And if you didn't notice it on your way in, if you go out that door, we have the mosaic up there of the cropped image for you to look at and see the 100 million stars in Andromeda for you to have a look at. It's only going to be here tonight, okay? That mosaic isn't a permanent display here. You just happen to come on the right night and when we get to see that. Okay? All right, so that is our news summary. I went on a little bit long, but you can see we had two really, really cool things to talk about today. All right, so
Jason, you want to come up?
So our speaker tonight is Dr. Jason Tumlinson, also of the Space Telescope Science Institute. And I forgot to get his resume, but I tend to find that these audiences don't really care about your resume because they know you're a fantastic and wonderful, wonderful guy. He's been here, what, 10 years now?
Not right, 7.
7 years, okay, well, you know. And he was going to talk to us tonight about the future of space astronomy and the amazing new things that we're going to be able to do over the next couple decades. Ladies and gentlemen, Dr. Jason Tumlinson.
Okay, I just need to test out my equipment here.
Okay.
What's the solution to that?
That was plugged in. Yay, you got it.
Plug it in. All right. I am going to try to make up in long-term vision what I lack in enthusiasm with respect to my colleague, Dr. Summers. He's a tough act to follow. But I want to spend about 45 minutes here telling you about in some ways, the last 300 years of astronomy and the next 30. Where we've been and where are we going in terms of the biggest questions we can possibly ask. Well, astronomy asks big questions, naturally. We're thinking about big things, right? Asking big questions. I'm going to talk about two in particular. Where did we come from? And are we alone? Now, this is more general, bigger than just how do galaxies form or how do planets form. These are really, these are civilizational scale questions. These go back forever, right? And they'll probably go far into the future. These are questions that have been asked as long as people have been doing astronomy. Of course, naked eye astronomy started as soon as the first caveman looked up into the sky, but telescopic astronomy, using actual telescopes and lenses, began with Galileo Galilei, officially in 1609. Here he is demonstrating his little telescope for the Doge of Venice in that year. And one of the things that Galileo is famous for discovering, among his many epic-making discoveries, was the satellites of the planet Jupiter. So there's Jupiter, and there's the 4 Galilean satellites, we call them, along with the well-dressed Italian. And this was really the piece of evidence that convinced people in Europe in the Renaissance and then eventually worldwide that there was a whole world out there beyond the Earth. It was not merely terrestrial. It wasn't just human. There was this otherworldly universe out there that we could actually learn something about. I told you this was going to be a fast history. We're going to skip ahead by more than 100 years now. I chose to illustrate the next advance with a brother and sister team named the Herschels, William and Caroline Herschel. By the time of the Herschels, they were building reflecting telescopes, actually invented by Newton, but William Herschel had a 40-inch aperture with this big rotating apparatus that pointed it around at the sky. The Herschels are famous for having discovered the planet Neptune, not known to the ancients. This is William Herschel's drawing of what he thought the Milky Way galaxy must look like, from looking at the band of stars on the sky and trying to figure out how that would look if we weren't living inside it. It's not that bad, but I think you can compare Herschel's image of a disk galaxy with Hubble's image of a disk galaxy in the lobby and see that he was doing pretty well for his time, but we can do much better. There's a whole other technique of astronomical observation which becomes absolutely critical a little bit later, so I want to introduce it rather early. That's called spectroscopy. You can maybe imagine what this is. There's Newton with his prism, right? Everybody's played with a prism when they were a kid or something, You hold a prism up to sunlight, what do you get? You get a rainbow, right? Roy G. Biv, red, orange, yellow, so on and so on. That is the fundamental technique that we still use today. I use it in my daily life as an astronomer to figure out what stuff is made of. And the reason is, if you take a spectrum like this is essentially the same kind of measurement as Newton's prism. If you take a spectrum like this, or like this is one of the first that existed by the Germans Fraunhofer and Kirchhoff in the 1800s, you can look for these lines. See these lines? This is a solar spectrum, and if you see these lines, that's absorption. That's an atom of a particular kind in that environment absorbing light, so the light doesn't get to you. This is the light that comes out of the sun, the ultraviolet, the blue, the green, the yellow, the orange, and the red. But where it's absorbed, the spectrum goes black. And that's for instance how we know that the sun is made of hydrogen and helium and has some iron and carbon and nitrogen and oxygen and all that interesting stuff. Spectroscopy is the way that we do the physics side of astrophysics. We figure out what stuff's made of, what its dynamics are, from taking these spectra. That's Newton's telescope, by the way. Okay, forward into the 1920s. This is Edwin Hubble himself. And he used this telescope here at Mount Wilson, which is 100-inch, to do what he's famous for, which Frank just mentioned, which is to measure the expansion rate of the universe. Now, he did that by observing exactly the stars, some of the stars that Frank mentioned, the Hubble variable stars. If he knew how fast they brightened and dimmed, he could work out the distance. Using spectroscopy, he could work out their velocity by measuring what's called the redshift. As an object recedes from us, it gets redder. As it moves towards us, it gets bluer. And Hubble was able to take redshift and distance and work out that the entire universe was expanding. That's why he's as famous as he is. That's why we named our first space telescope after him. Here we are. This is Hubble. This is the outdated version of what you just saw. I didn't want to steal any thunder. But here's Hubble doing its thing. This is the ultra deep field taken with Hubble's advanced camera for surveys. There's thousands of galaxies in there. I think this one right here, that's the only object in the field that's a star. Everything else is a galaxy. This is to date the deepest picture of the universe that Hubble, and therefore anybody, has ever taken. So that brings us up to almost the present time. We figured out first of all, thanks to Galileo, that there was a universe out there to learn about that wasn't terrestrial. We figured out that we could discover objects beyond what the naked eye or even small telescopes could see. We could see the outer planets. We could see parts of our own galaxy that we live in. Hubble showed us that the universe has a cosmology, that it has a dynamic all of its own, that it's expanding, that there's a history to the universe, that it had a beginning point. It hasn't always been here. All of those things flow from Hubble's discovery of the expansion of the universe. And probably the most epic-making or significant from the historical point of view discovery in our lifetimes has been the discovery that there are planets orbiting other stars in our own galaxy. This came around 1995 with the first discovery of what's called an exoplanet, a planet around another star, by a Swiss group of astronomers using a telescope in Switzerland. And what's really important about this is that they used this same technique that I introduced, spectroscopy, right? So let's go through this in a little bit of detail just to show you how it works. Here we have a star and a planet, star and a planet. And the star and the planet orbit their common center of gravity. That's one of Newton's laws of gravitation, is that any two objects orbiting will orbit their common center of gravity. That means the star, even though you think ordinarily the planet's orbiting the star's fixed and the planet moves, but it's not quite that way. The star has a reflex motion. It moves a little bit in response to the gravitational force of the planet. So the star wobbles back and forth just a little bit, right? And that's illustrated here in the fact that there are two pictures of these stars. When the star's moving toward the Earth just a little bit, the light gets slightly blue shifted. And when the star's moving away from the Earth just a little bit, it gets slightly red shifted. And so by watching the stars wobble back and forth, just like this, these astronomers were able to prove that there was a planet there. We still can't see that planet. We can't take a picture of that planet yet. That's what we're driving at. But you can prove that the planet's there by measuring the motion of the star that's gravitationally introduced by the planet. That was the greatest astronomical discovery of my lifetime, arguably. People would tell you that the acceleration of the expansion of the universe is equally important. There's a Nobel Prize for it out in the lobby, but I think this one's right up there. And this has kicked off a whole revolution in the way astronomers think about our field and the way I think the public thinks about our field, because this is addressing some of the deepest questions that we can address. Like I said, are we alone? Is there any other life out there? So where do we stand now? That was the last 300 years. I'm going to talk a little bit about the present in the next 5 to 10 years, and then I'm going to tell you what we see coming down 20 or 30 years from now. It happens that we're all fortunate to live in what really is a golden age of astronomy. And the reason for that is that funding agencies and the public have bestowed on astronomers an incredibly rich array of frontline instrumentation. The kinds of things that were far, far beyond the imagination of those early astronomers, even Hubble, who lived in the 20th century. There's the giant space telescope named after him. There's the Kepler Observatory, which looks for planets. I'll say more about that later. The Chandra X-ray Observatory. This is a UV satellite called ultraviolet imaging telescope called GALEX. There's the Spitzer Space Telescope, which is still going after about 11 years. That's an infrared space telescope. There's the European Herschel mission. There's a huge number of 8 to 10 meter telescopes on the ground, the Very Large Telescope, the Keck Observatory. We have lots of radio facilities like the Very Large Array. When you add all of these things together, you can see, you've probably seen, since you're all probably paying a bit of attention to this, you can see the discoveries of these things come together and mix and teach us new things on a daily basis. We really live in a real revolutionary period for astronomy, and we're fortunate to do that. I would like to be able to spend 10 or 15 minutes telling you about everything that Hubble has done that's awesome. It would take me a lot longer than 10 or 15 minutes to get through all of that. But what I think I will do instead of that is just point out the fact that Hubble is turning 25 years old this year. And that's amazing for any space satellite of any kind. The fact that we've managed to keep Hubble operating as an observatory for that long, and not only that, but make it better every 5 years, thanks to the human servicing, has made it by far the most productive astronomical observatory of all time, and arguably the most productive scientific facility of all time. Because it's turning 25, everybody here in the building is going crazy planning all kinds of events and talks and presentations, and we have a whole conference devoted to this. So instead of saying, here's Hubble's greatest hits over the last 25 years, I think you should just follow this website, and you'll see we have great video presentations coming out. We're going to have a big splash in April when the birthday actually rolls around. It's going to be fantastic. So I'd rather spend more time talking about the future than the present. So I'm going to move on to the immediate future for us, the Hubble 2.0, so to speak, which is what we call the James Webb Space Telescope. Now, if you look at Hubble, here it is, and then you look at JWST, they don't look anything like each other. Nothing, really. I mean, except that there's a mirror there, and there's some instruments in the back, and there's some electronics. They're very, very different beasts. The reason is, Hubble's not only 25 years old, but it's a giant steel tube with a big piece of glass in it, right? If you go out in the lobby on your way out, and if you can make it past the Andromeda image, back into the outer lobby, you can see there's these banners hanging from the walls, and there are pictures of the Hubble and the Webb primary mirrors to scale. So you'll see the Hubble primary mirror about 2.4 meters across, which is about like this, and the Webb mirror just dwarfs it. It goes all the way to the ceiling, and it's so big that we can't actually print it on a banner. It's just a piece of it. So I suggest you check that out on the way out. Hubble is designed to be a telescope that's optimized for observations in the infrared wavelengths. Those are wavelengths beyond what you can see with your eye. You know, light becomes blue and then green and then red, and once it's past red, you can't see it with your eye anymore. There's some insects that can, some probably nocturnal animals that can, but humans can't. The reason we're doing that is to pick up a bunch of stuff that we can only see at those wavelengths. I'll go through a bit of the science case. This is a zoom on Hubble's deepest image, that ultra deep field that I showed you. And then at the end here, we're going to try to re-simulate that image as it would appear for JWST. So there it is transitioning to what JWST sees. You see it's a sharper image. That comes from having a larger telescope. But not only that, not only do our pictures of galaxies get sharper because we have a larger telescope, but we can suddenly do all kinds of science here that we couldn't do before. These galaxies, the red ones, the old ones, the really distant ones, become much sharper and much more easy to detect. Just let that one run again, because it's kind of cool. JWST, in the same time, will be able to go almost a factor of 10 deeper, so take images that are detecting objects about 1/10 as bright as what Hubble can do in the same time. It's going to be pretty amazing. My personal favorite science case, this is something I actually plan to do with JWST once they hand over the keys, is to look at very dense stellar fields. This is one of those globular clusters that Frank pointed out in the image of Andromeda. This is a globular cluster in our own galaxy called Omega Centauri. You see there's just, this is actually not a Hubble image, but close enough. This is a Hubble image in here, and you see it breaks up into individual stars, right? Blue star, red star, blue star, red star. JWST is going to have this amazing device on it called a microshutter array, which is this array of little electronic doors. And we can open and close those doors at will and take observations of individual stars. So we can open that door to take an observation of that star, open that door to take an observation of that star, and just leave the others closed. So we can pick out stars to observe in these fields. We can work out their age, we can work out their metal content, we can work out what this cluster came from and where it's going, all from taking spectroscopy of these very dense fields. This is the scale of those little electronic doors at the scale of a human hair. So pluck out a hair, hold it up and say, they made 250,000 of those little doors smaller than a human hair in the space of about 3 inches square. It's quite a device. By the way, it operates at 300 and something degrees below zero, too. JWST as an infrared optimized telescope is going to turn images that look like this one, very much like the pillars of creation that Frank just went through, into images that look like this one, right? In other words, peering through this obscuring dust to see the star-forming regions, the young stars right there, and the jets that they power. We're going to start seeing hundreds of images of star-forming regions that look just like this with JWST. So once we have done that, and I should just say, this is something that hasn't happened yet, right? JWST is supposed to launch in about 3.5 years at the end of 2018. We expect it to operate, we hope, for 10 years. So that'll carry us through almost the end of the next decade, 2028, 2030 perhaps. JWST, like any telescope that's come before it, it's intended to revolutionize things. It's intended to bring us knowledge that we never had before. And more than that, if it's anything like Hubble, it's going to teach us to ask questions that we never thought. In other words, the thing we build it to do is actually only a bit of what it does. Most of what Hubble's famous for are things that its designers never imagined. They're questions they never thought to ask. And that's because as science moves along, you come up with new discoveries, and every new discovery raises a new question. So it's very hard for us to predict where our field is going to be in 2028 at least when it comes to deep infrared observations of the universe. So where do we go from there, right? Once we've got JWST, and we definitely will get it, where do we go then? Well, I like to motivate our work with this really fantastic quote, not from an astronomer, it's a biologist, a rather famous biologist at Harvard, Ed Wilson, famous for ants, actually. He's written a lot of wonderful books about science generally and his life as a naturalist. And his claim very recently was that the most important experiment in biology is the search for extraterrestrial life. Think of this. This is a world-famous biologist telling us that the most important experiment in modern biology is an astronomy observation, right? That tells you something very important about where our field is going in the next decades. And it's not just Hubble, it's not just JWST. NASA has deployed and will deploy a whole array of missions at a smaller scale. These are not the giant, multi-billion-dollar flagships, but it has deployed the Kepler mission, and there are two coming down the pipe called TESS and W first after that I'll speak about briefly in a moment, which are designed to address this problem that Wilson has posed. How can we find planets? How can we find planets that might be bearing life? And how can we find out if life is actually there? So we're on a pathway. Kepler's great discovery has been of Earth-sized planets. Kepler's been very good at finding all kinds of planets, but it's especially good at finding Earth-like planets. And it's done that with exactly the same, it's done that with an observing technique that I'll describe in a moment, called transits. But the real important observation is that 1 out of every 5 sun-like stars has an Earth-like planet. 1 out of every 5 sun-like stars has an Earth-like planet. If you go back after the Andromeda image, you're going to see millions of sun-like stars. That suggests that there are probably millions to hundreds of thousands of stars with Earth-like planets in that image, right? Just statistically, right? In our own galaxy, there are probably millions to tens of millions of stars with Earth-like planets. That is a discovery that even those astronomers who discovered the first exoplanets couldn't really imagine. This is a very new result. This is as of 2014. Well, we're not only looking for Earth-like planets if we want to solve Wilson's puzzle. We're looking for Earth-like planets in what we call the habitable zone, right? You might think of this as a bit of a Goldilocks problem. If a planet like the Earth, let's say, is at the position of Venus in our own solar system, or even worse, Mercury, it's not a comfortable place where you might want to go to the beach or play golf. It's like Mercury, where it's 700 degrees during the daytime and 700 degrees below, or 400 degrees below zero at night. It's not habitable. It's too hot. While if you're at the distance of Mars or beyond, also not good for going to the beach and golfing, it's too cold. So the habitable zone is more or less defined as where the radiation from the sun is just right so that water is in liquid form at the surface temperature. Because water is the key ingredient of life. It's 70% of all of our bodies. It's a bummer if the 70% of your body that's water freezes. So in order for a planet to be called habitable by the astronomical standard, it has to be in that region where it's not too close to get too hot and boil off all the water, not too far away to get too cold and freeze all the water. It has to be in this habitable zone, the HZ, habitable zone. So we have missions that can find Earth-like planets. Kepler has done it. We have a definition. We understand where those planets should be around their stars to be habitable. Once we've found them, how will we answer this question? Is there anybody living there? Is there life there on that planet? And it turns out this is a pretty straightforward problem when you think about it. It's a challenging observation, but it's a pretty straightforward problem. And that's because if you take a spectrum, just like Newton's spectrum of the sun with a prism, just like Fraunhofer's spectrum of the sun with his grating, there are features in the spectrum of the Earth that betray the presence of life on the Earth. We call them now biomarkers. It's a marker for a biosphere, a biomarker molecule. The easiest one to pick out, if you have the correct wavelength range covered, is the water vapor. These big divots in the spectrum here are from water. I think my next one is a little better. Nope, okay. These big divots in the spectrum here are from water. Light hits the Earth's atmosphere. Some of those photons from the sun get trapped by a water molecule and never go anywhere again. They get re-radiated into the infrared. So those photons, that light drops out of the spectrum, and it shows up just like that. There's also here the effect of the dust in the atmosphere, and then the ozone in the atmosphere, which is what protects us from the ultraviolet radiation. That introduces a very clear-cut drop in the spectrum. There's oxygen, the molecule we're all breathing to live, has these little signs right in there. Ozone is itself a very important biomarker because it doesn't exist with these other molecules in the absence of life. Ozone is a very clear signature that you have biochemistry going on. And then finally, these other things, carbon dioxide and methane, which are produced, carbon dioxide mainly by living people and then consumed by plants and then consumed, oxygen is consumed by us. Methane is another case where it's either emitted by bacteria or by animals. So if you can detect all of these biomarkers in the spectrum of an Earth-like planet in its habitable zone, you have the answer. That tells you that on that planet at least, there's strong evidence that there's life there, creating these signatures which otherwise would not exist. This is not what Mars looks like. This is not what Venus looks like. The uninhabited planets in our solar system don't look anything like this. The Earth does because we live here along with a lot of plants. So one way to detect a biomarker is to use the method that Kepler has used to detect planets, and that's the so-called transit method. This is an illustration of it. It's pretty cool, actually, to see. If you have a star, and you have a planet orbiting that star, if it's oriented just right? If the orbit of the planet is more or less in the plane that you're looking in, that planet will pass in front of the star, and it will make an image of the star just a little tiny bit brighter. Like it'll take 1 in 10,000 of the photons out of the image. So you'll have to, if you can measure 1 part in 10,000, you can detect this. And you can then measure the planet's atmosphere if the planet passes in front of the star by looking for these spectral features in the light that passes from the star through the planet's atmosphere and into our telescopes. So this is one way to detect these biomarker molecules, but it only works if the planet transits, right? It only works if this happens. If the star and the planet is oriented just so that the planet every once in a while passes in front of the star. If it's oriented a different way, where you say you have the star and the planet's going around it like this, it never actually passes in front of the star and it doesn't work. And that's actually the case most of the time. Because the orbits are just random, you have to be lucky for them to transit like this. So that's probably not going to be the way that we figure out, at least for lots of nearby planets, whether they have these biomarkers or not. Right? But anyway, this is a technique that we will use with JWST. Going back to that fantastic observatory. JWST may be able to use this transit technique to detect some biomarker molecules, especially water and methane, on what are called super-Earths or water worlds. So something that's 2 times or 3 or 4 times the Earth's mass, rocky in the core but surrounded by a big ocean. JWST might be able to detect water and methane on those planets. The spectrum would look like this, and I know this appears to be a total mess, but it's a simulated spectrum, by the way. This is not real data. One reason you know that is that the telescope is still in parts on the ground. And number 2, it looks a little better than real data actually would. But this is a simulated spectrum with JWST because, believe me, all the astronomers are ramped up. We're thinking about it. Even though it's in parts on the ground, we're launching it in 3 years, and we're ready to go, right? So we have to start thinking about what we're going to find. So JWST may be able to reach these water world planets, but it's not going to be able to get to genuine Earth-like planets, just like the Earth, one Earth mass in their habitable zones. And it's certainly not going to do that for a large number of planets. So it's a step in the right direction. It's a way to prove that the techniques work. It's maybe a way to make an important discovery. There's a water world out there with something to look at, but it's not really the answer to Wilson's claim. So what is the answer? What is going to get us this evidence that there's a separate evolutionary pathway for life, there's been a separate origin of life on another planet in our galaxy? The ultimate goal really is another living Earth, like our own. We already know, school children on Earth already learned that there are these worlds orbiting other stars, and what we'd like is for the future generations, and I don't mean the distant future, I don't mean 1,000 years from now, I mean my children, right? Possibly their children, but probably my own, right? Next generation school children. To know with the same certainty they would know this, right, that there's life on some of those worlds. An increasingly large number of astronomers, myself included, that's why I'm here, but a large part of our community has come to the view that we can actually do this within 2 decades. Because we're starting to see it. We have the technology. We have the ability to build a telescope that can do this. So how will we do it? Well, it's much different from what I said Kepler does and what JWST will do. Because what we want to do is break open this restriction of having to have the planet pass in front of the star every once in a while. That doesn't happen very often for typical stars. Statistically, we've worked out that 20% of sun-like stars have planets, but that's by extrapolating from a much smaller number of measurements with Kepler. So the way to really prove this works is to just figure out a way to take a picture of the planet. Go out to the 1,000 nearest stars, find the planets there, and take a picture, right? That's worth 1,000 words. So what we're going to try to use is an instrument called a coronagraph. And I don't want to get all into all the technical and optical jargon that's involved here, but basically what you do is when you point your telescope, you put something in the way that blocks the starlight so you can see the planet. Now I have here an illustration using a star, a bunch of planets in the habitable zone around that star. It wouldn't have that many. They would all gravitationally eject each other. But that's just a model. And the idea is to have the coronagraph block the starlight, for a reason I'll explain in a minute, so that you can see the planet. Now, we already do measurements with things like coronagraphs. In fact, they were invented to study the sun. If you want to study anything near the sun, like the corona of the sun or a comet, that happens to be a comet right there. This is from a NASA solar mission. You have to block the sun out because the sun is the brightest thing in the sky, right? You wouldn't see anything near it if you didn't block it out. So people have figured out a way to block out starlight to see stuff nearby, and that's what we intend to do. The idea is to null out the stars so you can see the planets there, right? But it's really, 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 really hard, right? Because the planet is 10 billion times fainter than the star you're looking at. Now, the kinds of stars we're talking about are literally the kinds of stars you can see if you walk out into the street, San Martin here, and look up. They're that bright. They're bright stars. They're not the 28th magnitude stars that you're seeing in the Andromeda image in the lobby. These are bright stars. But the planet, because it doesn't emit any light of its own, it's only picking up the light that the star shines on it, right? It's picking up Earth shine, right? It's 10 billion times fainter than the host star. So how in the world are you going to take a spectrum of a thing that's sitting right next to something that's within, a tenth of an arc second of something that's 10 billion times brighter? This is a real engineering challenge. Right? In fact, this problem, detecting an Earth-like planet in its habitable zone, a tenth of an arc second away from a bright star that's 10 billion times brighter, is actually no harder than this problem. So if you figure out how to solve this problem, you can figure out the planet, right? It's this problem. Let's put a telescope in Baltimore, and let's put a searchlight in Los Angeles, and then let's put a firefly next to that searchlight. If you can solve the problem and find the firefly for all the searchlights in Los Angeles, from Baltimore, you got it fixed, right? It works. That's how challenging this problem is. I don't want to minimize the challenge involved here, and this is why it's going to take us 20 years to get to this point, but it's actually something that people who build instruments and work with telescopes on the ground in space are spending their careers trying to figure out. We have a whole group of people here in what's called high contrast imaging. Believe me, this is a high contrast, faint thing and a really bright thing. They're looking for the fireflies in the searchlights. So I think we can do this. What will it take? Well, ta-da! The mission I've been teasing all along is something that we've started to call the High Definition Space Telescope. It would be a new space telescope following on JWST. It would orbit at the Earth-Sun L2 points, so the same place JWST is going. It's sort of a gravitationally happy spot, 1 million miles beyond the moon. We'd like to see an aperture for the telescope of 10 to 12 meters, which is about the same size as the room here. So, you know, not small. More like the room in this direction than that one, but still, it's big. It has to be a deployable mirror, just like JWST, so it'll all fold up origami style and fit in a rocket. Covers ultraviolet to near infrared wavelengths. We'd really like for it to be more like Hubble and less like JWST, so that robots or astronauts could go in there and replace the instruments. That's been the reason that Hubble has been so successful over 25 years. That's the reason it lived that long. So that's what we'd like. And of course, these things take time, so we're looking at 2 decades or so before we can launch. This is the comparative mirror sizes. There's the Hubble mirror. If you go out in the lobby, as I said, you can see that banner that tells you how big it really is. That's JWST to scale. And our high definition space telescope is this 12-meter thing. It's pretty big. Okay, so why does it need to be so big? Let's take the stars within 200 light years, which is about 70 parsecs. That's all the stars that's from the list of actual stars at that distance. Okay, that's our galactic neighborhood, and the sun's in the center. Okay? Let's now say, well, we know that about 20% of those have Earth-like planets. We don't know which ones, but let's just randomly pick 20% of them. If you only build a 5-meter telescope, you only got a few, right? But if you go to 10 meters, now you're starting to talk about real numbers. And the reason that matters is that we don't have to be lucky. It's possible that of all the Earth-like planets, if every Sun-like star has an Earth-like planet, it might be that only 1% of those have just the right conditions to have developed life, to have these biomarkers, to have bacteria and bipeds, right? So we don't want to gamble too much, right? If you're going to build a big telescope and launch it into space and really, spend a lot of money and waste a lot of people's time, you don't want to gamble on just doing it with 10 planets, because let's say if only 1% of those planets have life and you only roll the dice 10 times, you're not going to win, right? So what we want to do is roll the dice enough times that we know we're going to come up, or we can really predict confidently we're going to come up winners, even if the dice are loaded against us. So it turns out the number you really need is more like 50 to 70. We'd really like 100 planets. And that forces us to these very large apertures because we have to use stars that are progressively further away and planets that are progressively fainter. So that forces us to be in this region between 10 and 12 meters to pick up 70, 50, 70, 100 planets. That's a 10 or 12 meter telescope. That's, as I said, that's critical because we don't know the actual rate of life on these Earth-like planets. And we have to improve our odds by aiming high. Okay, so it's a simple equation between a large telescope and 50-ish Earth-like planets. Maybe life, we don't know. We have to first find these by going to the star, nulling out the starlight, imaging the Earth-like planet, taking a spectrum, and hoping that we get this spectrum, right, with the water, the oxygen, the ozone, and the methane. That would be the grand prize. That would be the spectrum of the Earth-like planet and the habitable zone of its star, showing biomolecular molecules, and that's going to be, in the newspaper, right? I chose my birthday in 2035 as the day that the discovery is announced. I guarantee you will never see a spectrum like that. They'll show some artist's conception of the planet because they never show spectroscopy in the newspaper. Presumably Bob Dylan's not going to have a new record out that same day. It'd be like 98. But that's not all. You're not only discovering Earth-like planets with potentially life on them, but you are going to completely revolutionize the rest of astronomy, right? A 10-meter telescope in space, a 12-meter telescope in space. This is a big deal. And it tells us all kinds of things we didn't know before about galaxies, stars, everything you can think of. And what it really does is follow through on this promise by Riccardo Giacconi, who won the Nobel Prize in Physics in 2002 for inventing X-ray astronomy. He was also the first director of the Space Telescope Science Institute. 21st century astronomers are uniquely positioned to study the evolution of the universe in order to relate causally with the chain of causes, the physical conditions during the Big Bang to the development of RNA and DNA, our genetic material. And there really is an actual link between those two things in the way that I'll describe. So the frontier for astronomy is not only to discover these Earth-like planets and prove there's life there, but to figure out how we got there, right? Which is the same way that we got here. And I like to illustrate this profound fact with the answer to a question that Neil Tyson was asked, I think, on a radio show. It's actually a pretty cool YouTube video if you dig it out. What is the most astounding fact you can share with us about the universe? It wasn't his vest. It was the knowledge that the atoms comprise life on Earth. The atoms that make up the human body are traceable to the crucibles that cook light elements into heavy elements, and all the fundamental ingredients of life itself. That's the fusion of hydrogen to helium to carbon to nitrogen to oxygen in the interiors of stars. These ingredients become part of gas clouds that form the next generation of solar systems, stars with orbiting planets, and those planets now have the ingredients for life. So that when I look up at the night sky, and I know that we are part of this universe, we are in this universe, but perhaps more important than that is the fact that the universe is in us. You may have heard we are star stuff, and that is literally true. All the carbon, all the nitrogen, all the oxygen, all the magnesium, iron, everything you can think of here in your bodies in the room came out of a star. That's pretty profound. It's so profound that it has a t-shirt, right? You are here, right? But what we're really saying is not you are here. That's true. You know, we're here. We're in a galaxy. It's more like you were here, right? The stuff in you used to be in a star. It used to be in the interstellar gas. Some of it used to be in intergalactic space because galaxies like to eject material out into intergalactic space over time. So this whole story of the origin of life goes through the intergalactic medium, galaxies, the interstellar medium, supernovae, right? You used to be part of a supernova explosion at some point. This is the whole story of cosmic birth to living Earth. So I want to very briefly go through this evolution from protogalactic seeds through the birth of galaxies, through star clusters, through planet forming into the solar system to tell you how this telescope, this same telescope that's potentially going to discover life on other worlds, is going to blow open this whole story of how that life got there and ourselves, right? And it's actually pretty amazing to think that even if the life we were to discover were to have, 7 heads and to drive on the other side of the road, we would still have this in common, right? We all came out of the same basic cosmic origins, stars, galaxies, and planets. However, whatever language they speak, even if they're just unicellular bacteria, we at least have that to talk about. What we're calling this JWST does an amazing thing. It improves the resolution with which we can observe the universe by more than a factor of 5 in one dimension and 25 in another dimension over Hubble. It allows us to resolve very important thresholds. And I like to illustrate this with a very simple analogy, right? The gain in image sharpness between Hubble, which we've all been marveling about here, right? Go out and look at the Andromeda Galaxy. The image sharpness between Hubble and this JWST is exactly the same as between the standard definition TVs that in the 80s were encased in wooden boxes, right? And the new ultra 4K HD TVs that you can still barely afford, right? It's a factor of 25 in image sharpness. And that's going to totally revolutionize the vision we have of galaxies, stars, and everything else leading up to life. I want to make this very concrete. So we have a great postdoc here who likes to make fake galaxies and compare them to real galaxies and figure out what galaxies are doing. And he's helped me to simulate a galaxy at redshift 2. So this is 10 billion light years away. It's 10 billion years back in time, this galaxy. Hubble has taken pictures of thousands of galaxies that look just like this, right? This looks like real Hubble data. It's a disk galaxy at this early epoch. If we zoom in to its star-forming disk, you really can't see much, right? It's a blur. Even Hubble, which is only 7, 8 feet across, can't make out all the detail. Well, I said JWST is going to fly, and that's true, and it'll do better. Its vision is sharper, but it only observes in the infrared. So it's going to miss a lot of the important light, especially the youngest stars. The blue stars in the Andromeda image out there, those are the youngest stars. They wouldn't really show up in a JWST image that's like this. So it's still, even though it's a sharper picture, it's not capturing the whole range of what there is to see. But this, look at that. Compare that to this, right? night and day. That's a 12-meter telescope observing in the same wavelength range as Hubble. Right? Look at what you can see if you zoom in. Now you're seeing individual star-forming regions, all these little blobs. What used to be just a blur breaks up into individual star-forming regions. You can actually see what's going on there, right? These are the building blocks of galaxies. There's another one. See that little satellite galaxy? Pretty much gone, right? In the images from the other telescopes. So this unique spatial resolution from having this enormous telescope, this 12-meter telescope, allows us to resolve things at 100 parsecs, which is 300 light years, everywhere in the observable universe. Something we've never been able to do before. And that's going to completely revolutionize our ability to understand what galaxies do. Not only that, but actually I just lied to you because I said that was a galaxy. That's true, that's part of a galaxy. But the luminous parts of galaxies, the part you can see, are really only a bit of the story. If I skip ahead, there's a galaxy. But in fact, galaxies are surrounded by this very diffuse gaseous medium, which you can't see in images. It just doesn't light up in starlight. The stars aren't there. But this is the fuel that creates galaxies. And in fact, some of those heavy elements, the carbon, nitrogen, and other stuff that I mentioned earlier, used to be out here in this so-called circumgalactic medium, which found its way into a galaxy, formed stars, planets, people, Toyotas, and everything else. And we've never seen this stuff, right? We know it's there because we can see it absorbing light from the background, but we can't take a picture of it. This observatory will be able to do that. And so we'll be able to see that galaxies are actually surrounded by this rich medium of gas that's feeding them, that's receiving the products of their output. And moreover, this stuff recycles over billions of years. This gas goes in a galaxy, forms a star, gets kicked out again, comes back in this great recycling process. And we can watch that happen if we can fly this observatory. Not only that, if that's not enough, like the knife salesman says, but wait, there's more. At the resolution that this observatory can achieve, virtually every star in the Milky Way moves. Okay, so if you watch a star, you find a star, you wait 10 years, it'll move, right? The velocities we can resolve and detect are actually just kind of mind-boggling, right? Out to the nearest stars, you can detect motion that's as fast as a giant tortoise. Right, 0.2 miles per hour. So go to the zoo, watch a giant tortoise. If he walked for 10 years without stopping, and you put him out at 10 parsecs, and then you lit him up, you'd be able to see it. So I know that's a lot of ifs, but the point is, it's a really slow motion, right? Virtually every star is moving faster than that. Out to 100 parsecs, out to 10 kiloparsecs, which encompasses the entire disk of the Milky Way. We can detect stuff that's moving as fast as a Formula One racer. Out to the nearest galaxy, like the Andromeda galaxy, anything that's moving about as fast as the space shuttle or spacecraft does in orbit, also detectable motion. And this is amazing because it turns the entire galaxy into a movie, right? You can now study not only the static universe, what stuff looks like when you take its picture, but watch its motion over time. So imagine taking that Andromeda image in the lobby there, and seeing it in motion, and seeing all the motions of the stars, and watching all the dynamics of the stars moving and forming over time. It will be possible to do all of this in the future. We'll not only be able to do that, we'll be able to measure the masses of stars, the individual masses of individual stars all the way out past Andromeda. We'll be able to see stars forming in environments where we currently can't. This is a Hubble image of the star-forming region called 30 Doradus. It's in one of our own satellite galaxies called the Magellanic Clouds. And Hubble sees just a blur there. Frank was showing you earlier, a lot of those star clusters in Andromeda are they just become a continuous blur in the center because we don't have the resolution to pick it out. JWST is going to be able to see that, break into individual stars, count them, and work out what their masses are and how they got that mass. Finally, one of my favorite topics is the solar system. We went all the way to the edge of the universe, and now we've come all the way back. But this is just as much a part of origins as anything else. A lot of these outer solar system objects when we figure out what they're made of, they tell us what some of the oldest components of the solar system are. They tell us how much carbon and nitrogen and oxygen there was in the early solar system when the Earth formed. And they tell us much about the history of our own planetary system that we didn't know before. If you take an image of Pluto with Hubble, it looks like that. Not so great. You can barely make out the fact that it's not a uniform surface. But if you were to do it with this 12-meter telescope, suddenly you can actually see surface features. We can resolve features in the outer solar system at the orbit of Jupiter that are as large as the island of Manhattan, say, right? Which is pretty small, 20 kilometers. One of the coolest things you can do is watch stuff happen on the outer planets. So this is a Hubble observation of the disk of the Galilean satellite. We're now going all the way back to Galileo. He discovered this satellite of Jupiter called Europa. It's the ice world. You've probably seen it in Hubble pictures. Hubble also discovered that it has geysers, right? So those giant ice plates crack open and jets of water vapor come out. This one is probably about 200 kilometers tall. What is that, 120 miles? That's a pretty tall geyser. But we can't actually say exactly how tall it is because Hubble just sees a little bit of an indistinct blur, right? Again, it's a problem of resolution. If you had a bigger telescope, suddenly you can see the structure of those objects, follow their evolution over time, and learn a lot about the outer solar system, even without sending a spacecraft there, which we often do, right? It's great we send spacecraft out there to live in the outer planets for years, but you can't do that for every planet. You can't do it at all times. If we have telescopes here at Earth, we're pretty competitive with the image quality you can get. So there's a lot of amazing stuff you can do with this telescope, apart from finding life, if that's not enough for you. What can it do in particular? Well, you can resolve every galaxy in the universe to 100 parsecs or better. That's 300 light years. You can detect virtually every galaxy that's forming stars at the epoch when our own Milky Way formed, which means you're going to see all the Milky Way's building blocks and the entire history of galaxies like it up through the present. We can observe individual supernovae all the way back to the beginning of the universe. We can see this nearly invisible gas feeding galaxies and receiving their products and recycling. We can watch the motion of virtually any star we choose in a local group of galaxies. And we can see objects the size of Manhattan, the orbit of Jupiter, including those big monoliths. Which is ultimately going to allow us to draw this whole picture of cosmic birth up to life in the present time. So I just want to leave you with the thought that we're building on 400 years of astronomical history, right? Starting with Galileo's first attempt to put a telescope on the sky and figure out what was there, his historical and revolutionary discovery that there was a world out there to know that wasn't terrestrial. All the way through the astronomical pioneers of the last 2 centuries, through our present when we started to grasp the idea that there may be living planets out there, and to think that we're, with 400 years of this history behind us, possibly only 20 years from discovering that life, is a really amazing idea to contemplate. So I'm excited about this. I hope I've got you a little bit excited about this. I'd like you to try to follow our progress as we go along. In particular, the Institute has a site called searchforlife.net where we post a lot of the developments in this field, as well as some more in-depth material about this particular telescope. And there's the usual websites for tracking what the Institute here is doing. I hope that was enjoyable, and at that point I'm happy to take any questions you have. Thank you. It's the end, get it, right?
It's a soft capture mechanism.
Yeah. That's not funny.
Okay, I have a question down front here.
In the search for life, all scientists seem to assume that we need to be in the range of where there's water and so on. Well,
That's
let's
right.
even assume that we need liquid.
That's
Why
right.
couldn't life exist in a situation where the liquid was CO2?
Yeah, it's true. So we are making a big assumption when we talk this way, and it's you could remove that assumption, or you could explain that assumption by just taking basically everything I said, and when I said life, just say life as we know it, as we understand it, carbon-based, water-dependent, And that may be restricted with respect to the grand diversity.
Could
of
be
the world.
sulfur-based.
It's entirely possible. And people who study the origins of life here on Earth in these very extreme environments speculate that there may be independent strains like that here and elsewhere. So it's a very good point. And what I'm talking about is life that we have at least enough in common that it's carbon-based and depending on who we belong. That's true.
So, if you get out there with this and find this life, then you'll get the money. Pretty much, I mean.
We have to get the money first.
Yeah.
Yeah. Money.
Makes me think of the song.
Yeah.
Money.
All right. These are what we call flagship missions. Hubble is a flagship mission. Webb is a flagship mission. And in my view, they only exist because astronomers and the general public and Congress and every administration all came to the same conclusion, which is to make the great discoveries, you have to have the big gains in capability. And to have the big gains in capability, you have to keep pushing the envelope of the technology, and that's expensive. We're very fortunate, and we all are very fortunate, that our country and our government and ourselves have agreed to support science at this scale for decades. In the case of Hubble, we're talking about over its lifetime a total of about $20 billion. Now, in the grand scheme of things, that doesn't add up to much when you're comparing it to other things that the government spends its money on, right? But what I think you're getting out of that is more than worth it, because it's I like to use a quote. There was a Nobel laureate who discovered the cosmic background radiation. His name was Robert Wilson. And in the 1970s, he was testifying before Congress, and he was asked by one of the budget skeptics, Mr. Wilson, in what sense does your proposed observatory defend the country? And he says, sorry, it does not, but it makes it worth defending. So that's something to keep in mind when you're asked, why are we spending money on these things? It's because, in some sense, it's illuminating all of us, all of our citizens, all of humanity. I think it's worth it. Yes?
And you say repair a telescope at L2.
Right.
Is that robotic or
It is,
human?
yeah. It could be either. It's not very well known, really, but NASA has brought its robotic servicing capability to a pretty high level of readiness. Even to the point when, 10 years ago, when Hubble's last servicing mission was canceled after the Columbia accident, they seriously considered sending robots instead. Now, in the end, they decided that it wasn't quite ready at that point, but they've spent 10 years developing since then. So they have robots that look like people. They have arms and everything. And they take our astronaut friends, like John Grunsfeld, who used to be here at the Institute, who's been to Hubble 3 times, and they've had him remotely control the robot arms, and it works pretty well, right? On the other hand, NASA wants to go to Mars. They want to send people to Mars. And Mars is a lot further away than this Sun Earth ultimate one. So if you can build a rocket, you can build a spacecraft, and you can carry instruments to Mars, you can certainly take it to this telescope and do exactly what we've done with Hubble. Slide out the old box and put it in the new one.
In your slide on the biomarkers,
Yeah.
if you recall, you talk about the fingerprints. So are you looking at some footprints?
Well, that's a metaphor. We call it a fingerprint. We call it a fingerprint because that's a unique signature.
Yes.
Your fingerprint is a unique signature of you. This is a unique signature of life. It's just a metaphor that we use. And there's a lot of thought that's gone into those biomarkers because some of them, individually, like oxygen in an atmosphere, can come from a source that isn't life. But you can't get methane, ozone, and oxygen and water all at the same time unless there's some form of life there, as we understand it.
So there's one more question that I have is when you think of life, you think of Earth.
Right.
Because it's a habitable zone
Right.
and it harbors life
Right.
from a biological perspective. But when you talk about searching for planets, Earth-like planets,
Right.
with life, you're saying it may have only 10% or less.
It's possible. Yeah, we really don't know.
Why can't it be 100? If it
It
is
could
Earth-like,
be. It
that
could
would
be. It could be. Yeah, we just don't know. We know how many stars have Earth-like planets. We know roughly how many of those Earth-like planets are in their own habitable zones. What we don't know is, given the star's age, the energy input to this planet, the mass of the planet, the atmosphere the planet has, we don't know how any of those variables control the incidence of life. We know that on our own Earth, it took billions of years to get to the point where we are now, right? If we had observed, if you observe the Earth 500 million years ago, you wouldn't see any of this stuff. It wouldn't look like this at all, right? It would totally different. So it's a very subtle problem. And we have to be open to the fact that most of the planets we look at won't show us anything. Right? It's possible that all of them will, but we have to always err on the side of caution. Because we're going to, as I said, we're going to spend a lot of money on it.
We have a question back there?
Keeping with the theme of big general questions, in the hopefully near future, when we have a catalog of planets that have life as we know it, what do you envision we might do with that information? For example, would there be a way to communicate with those planets?
So one of the nice side benefits of observing planets and finding life this way is that all of these stars are really close. They're all within about 50 to 100 parsecs, which is about 150, 300 light years. Now, light travels at a finite velocity, which means that if you send them a radio signal, it takes 50 to 100 years to get there, so you better ask a good question and not an radio signal. But it's theoretically possible that you could maintain a conversation over such a long time. So that's talking to ETs. I should point out, I should not be over-promising, and I should point out that you can find life with these biomarkers, oxygen, ozone, methane, and it doesn't have to be people walking upright. It doesn't have to be little green men. It can be bacteria, right? But we at least know that there has been an independent origin of something living on that planet. They could be far ahead of us, they could be far behind, we don't know that. Another thing you can do is, in a more scientific sense, is you can take the planets where you see the biomarkers and then everything else you know about that planet and that star, and you can start to work out, if I see life, it's a star that's older than 5 billion years, and the planet's so-and-so in this orbit, and it's getting that much energy. You can start to work out the factors that actually made it possible. And that's going to nail down these things we don't know now, which is how frequent life is and under what conditions it actually develops.
Is it conceivable that there could be lifelike things based on something other than carbon?
As I understand it, that is chemically possible. That's outside the scope of what I've discussed, which has been much more conventional according to the definition that I was discussing with this fellow. But I understand that it's theoretically possible to have sulfur-based chemistries. That's right.
Over here.
Is there any, as you look at the structures you see as far out as you can see, and then you look at like CERN and high energy particle physics, is there any relationship between the two ends of the?
Not really. I mean, there's an area in between where people think about the cosmological consequences of particle physics at the energy scales that CERN probes. There are some high energy. There are theories based in high energy physics that explain the acceleration of the universe that's been discovered. There's not much bearing of high energy physics directly on the question of life and its origins and detectability, except to the extent that the universe has to make sense and be hospitable for life.
All right, any other questions? All right, one last one down.
This is a little different question. I apologize for it, but I'm so interested. You showed a picture of the Andromeda Galaxy taken in 1901.
Yes.
And of course, the whole, you didn't have able to make representations, there'd be no astronomy.
Right.
Okay, that was a beautiful picture. Would you mind telling us, how do you still have, was it on film? How do you still have it?
Thanks to the internet, I found it. There is, if you go to what the Project Gutenberg, I believe is where I found it. It was a book that was published before copyright was instituted in the United States, and it had so it was a 1915 or something book. No, I can't remember what it was. It was a book on natural history, and it had all sorts of illustrations, and it did have that 1901 Yerkes Observatory.
HD from today, didn't it?
It would have been taken on a photographic plate, so a glass plate with the
yes, but it was.
Yeah.
So I literally do a lot of searching on the internet to find my imagery, and that was what I happened to find, because finding those old photographs to compare to today's photographs is very important. And also to show the state of photography 100 years ago, 114 years ago, was, you know, still pretty good.
I think we have one last one over here for you.
Yes, this biosignature you're searching for.
Right.
At what level of technology we gotta get to? Is James Webb going to
Yeah.
get you any closer to that goal?
It does. It does in some fairly significant ways. So the thing we're learning to do with Webb, which we cross our fingers and hope works, is to build a telescope that's larger than what fits in a rocket in one piece. A deployable telescope. Anything that big and larger has to be launched, folded up, and then unfold itself autonomously. So that's one thing we're proving will work with JWST. That's called technology development or technology heritage. That'll lead to the next thing. But the real challenge is this 10 billion factor that I mentioned. It's getting the starlight to go away to throw, okay, well, let's just pick an example, right? We want to throw out the 10 billion photons, the particles of light coming from the star, and detect the one coming from the planet, right? These planets, by the way, when you go to the 12-meter mirror, you look at one of these planets, one particle of light, one photon from that planet is going to hit that giant mirror as big as the room every second. That's how faint they are. So the technological challenge is to be able to null out the starlight. It's like finding one person if you took everybody on Earth and tried to find one person, right? You have to.
Cosmic game of Where's Waldo?
Yeah, it really is. It really is. So it's
Excellent.
It's a game. The high contrast imaging is a very demanding game where you have to throw out that many photons, and the ones you don't want, and keep the ones you want. It requires very exquisite thermal and mechanical stability. Like this thing has to be totally still and quiet. And it requires optical manipulation of the light with some devices that actually, we have a laboratory down here that does this kind of stuff, so they're doing it on a daily basis. And we're projecting out saying, yeah, it's going to work in 5 to 10 years, but it doesn't work right now.
Okay, it's 9:30 and we usually cut off at 9:30, so I want to thank Jason again. And we will see you here next month, March 3rd, Dario Robleto, a wonderful conversation on the combination of art and science. See you all. Have a great night.
Carry cards.